In this lesson, we're going to start exploring quadratic relations. The standard form of a quadratic function is y equals ax squared plus bx plus c, where a cannot be equal to 0. And the reason for that is if a was equal to 0, this term would go away, and you're left with y equals bx plus c, which is just the form of a line, right? mx plus b. That's what we're used to seeing as a line. But this isn't a linear function. This is a quadratic function, so that a value cannot be equal to 0. Quadratic functions are degree 2. This means that when simplified or expanded, the highest exponent is 2. So if we look at example 1 here, they give us 3 different relations, okay? And they're asking us, is this quadratic or not? Now, looking at them, you think, okay, this is a degree 2, this is a degree 2, this is a degree 2, no problem. But once simplified, so if you look at a function, you need to simplify it all the way before making that decision. Now, this first function, a, is already simplified all the way. So this is degree 2, and it is quadratic. And all we're looking at is the highest exponent. Now, if we look at the second one, looks okay, but we should probably expand this, FOIL it out. So if you remember your rules for FOIL, this would become y equals x minus 4 times x minus 4, all plus 2. Multiply that out. X times x, that's your first, is x squared. Outside, x times negative 4. Negative 4x, your inside, negative 4 times x, which will give you negative 4x, and then last, negative 4 times negative 4 would give you a positive 16. Add the 2 to the end. Simplified, this becomes x squared minus 8x plus 18. Evaluate it again, take a look at it. Yes, there is only one exponent that is a 2. There's nothing that's higher than that. So this is also a function that's degree 2, therefore quadratic. Our last one, C here. Same idea. So we've already done the multiplication there, the FOILing out, but you've got an extra x in front of that. And you could probably anticipate, well, if I multiply through by an extra x, that means you add the extra exponent. So let's have a look at that. X, we've already done the FOIL, so that was this piece here in this previous function. Erase that so it doesn't confuse us when you go back. Oops. So that would be x squared minus 4x. Well, they combine. So minus 8x minus 16. And then you still have a plus 2 at the end. But we need to distribute that x in there. So this becomes y equals x cubed minus 8x squared minus 16x plus 2. And having a look at that, this is no longer a degree 2. We do have a 2 in there, but that's not the highest degree. That's not the highest exponent. So this function is now a degree 3, so that it is not quadratic. Will we be dealing with functions that are higher than a degree 2? Not in this course, but we will in Applied 4DS. So the graph of any quadratic function, we give it a new name. It's a parabola with a single vertical line of symmetry. Okay, so parabolas are kind of like an upside down U, but the arms go out and down or go out and up. So you're not looking at a straight up and down U like this, they always go out. Okay, notice that I put arrows at the end, and there's this vertical line that goes down the middle. That is an axis of symmetry. So if you folded your parabola in half, it would look the same on either side. And we're going to use those properties to to help us out. Okay. So a linear function draws a line, a quadratic function draws a parabola. Here's a little exploration activity that you might want to do with me, or may choose to hit pause on the video and try it out on your calculator first. I always suggest doing that so that you can see how this comes about. So it says, using your graphing calculator, graph the following on the same graph. Sketch the graphs. Be sure to label all intercepts. Make sure all stat plots are turned off. Press Y equals, input the equation, and then you hit zoom 6. So let's have a look. We've got 3 functions here. If I pull out my calculator, when I was talking about stat plots off, up top, if I move my arrow up, you can see I've highlighted plot 1 or plot 2 or plot 3. If it's highlighted and it looks like this in your calculator, that means the plots are turned on, and there will be incidences when we want to do that. But here we don't want to, so we're going to hit enter and make sure that the plots are all cleared off, and you have nothing in there from any previous questions you've been working on. So let's put in x squared, and x squared is going to be our parent function. What do I mean by that? Is we're always going to be comparing our graphs to x squared. So let's just have a quick look at that. So zoom 6 to see what that looks like. And there's that parabola shape. Okay? That's the standard, that's the parent function for a quadratic or for a parabola. Now let's go back into y equals, and let's see when we plot 0.3x squared. So if I put 0.3x squared, how does that look different? Now I'm going to hit trace because I've already done the zoom 6, so that should be fine. And what trace is going to do is going to allow me to see which graph I'm on. So there's the new one. And if you compare, if you press up, right, and down, you can jump from one graph to the other. And if you move your cursor along, you can see a little bit easier. So they both share the same point. We call that the vertex, right? They share the same vertex at 0, 0. But y equals x squared is narrower than y equals 0.3x squared. You can see that by changing that coefficient of x squared, we made it wider. So what's going to happen when I put a 5 there instead? You can maybe anticipate the result. If I put 5x squared and hit trace, there, and it is narrower. So again, move the arrow to the side and you can jump between your 3 graphs and you can compare them. Okay, so let's draw some conclusions there. Now as you can see, I've drawn my 3 curves, or my 3 parabolas on my graph. You can see they all share that same vertex of 0, 0. And I'm just going to label them so that you get an idea of which one's which. And that's good for your notes too. So this first one was y equals 5x squared because it's the most narrow. Then this is my parent function, y equals x squared, the one we're going to be comparing to all the time. And then my third one, y equals 0.3x squared, was the widest. So how does changing the coefficient a affect the graph of the relation? The larger the value of a, the narrower the parabola. The smaller the value of a, the wider the parabola. Let's take a look at the next part. So for b, we've got x squared, y equals x squared, again our parent function, and then y equals negative x squared. Now we're exploring how does changing the sign of a affect the graph of the relation. So let's go back to our graphing calculator. Now if you want to turn graphs off, I'll show you how to do that as well. So let's just clear these 2 out and put in y equals negative. Don't forget you're using the negative, not the minus. Negative x squared. And if we hit trace, you can see both graphs. And if you couldn't remember which one was which, you can press up and down. You can always turn one of them off. So if you go back to y equals, and you go to the equal sign and you press enter on it, it'll actually turn that off. And when you hit trace, you can see it's not highlighted anymore. It just graphs the one function. And if you want to turn that one back on, and you hit enter on the equal sign, and then do this one and turn it off, you'll just see our parent function. And if you want them both on, then you can do that. But you don't have to delete the function if you're exploring and looking at different things here. You can just turn the functions on and off once you have them written. So as you can see, what happens when you put a negative in front, they look exactly the same, and the x-axis actually becomes another line of symmetry between the two graphs. It's flipped over that line of symmetry. It's flipped over the x-axis. So instead of opening up, your parabola now opens down. So let's put that on our graph, and we can write out our concluding statement here. The width stays the same. If a is positive, it opens up. If a is negative, it opens down. Now what I'm looking for when you're drawing your parabolas is that there's a rounded bottom on your parabolas, not a pointy bottom. I'm looking for the arrows at the ends, and I'm looking for your labels, okay? If you're only graphing one parabola, then it's understood that that's the graph. But in something like this where you're comparing the two, you want to make sure you label them so we know the one that opens up, y equals x squared, one that opens down is y equals negative x squared. Let's take a look at C. In C, we're asked, how does changing the value of a b affect the graph of the relation? So if you remember at the beginning, we had y equals ax squared plus bx plus c. So this is the value we're changing now. Now it's not as obvious when you're graphing what's happening to the b, so let's have a look. Put these into our graphing calculator. So go back here. I can leave the first one because it says x squared plus 0x, which is the same as just x squared. Now you could put in the plus 0x, but that really, you can trace it and see. You can see that doesn't change our graph. It's the same as y equals x squared, that parent function. Let's try the other two. X squared plus 4x. And x squared minus 6x. If I hit trace, so that looks a little bit different. And how do I know which one is which? So maybe this might be an instance where, let's turn off this graph, that minus 6x, by just hitting enter on the equals and hit trace again. So you get your parent function and then our other one. Now the other one, if I press right down, x squared plus 4x. So what is happening here? It's not obvious, okay? So one of the things that we look at on our graph is the axis of symmetry. And the axis of symmetry always goes through the vertex. And now I'm just putting my cursor there. That's not the exact value. I will show you how to get the exact value, okay? But our vertex has moved, okay? Our vertex originally was at 0, 0, and now my vertex has moved to 2, negative 2 on the x-axis. Where is that coming from in my equation? I've got a 4x. Okay, let's go back and look at the 6x one. Let's turn that one on and turn this one off and hit trace again. Okay, my parent function, and then there's my other function. So that was x squared minus 6x. Well, it looks like instead of the graph moving to the left, my graph has moved to the right. It's also moved up and down a little bit, which is different, right? We're not used to it moving up and down. So far it has been flipping upside down and changing width. But what has happened to my line of symmetry? So for this function, the vertex has moved over to positive 3. So with the other function, if I turn that one back on, here, the vertex went to negative 2, and now in this new function, the vertex goes over to positive 3. Now when you look at the actual function up in the top corner, that's also backwards from what we're seeing. This is negative 6, not positive 3, and the other one is positive 4, not negative 2. So what exactly is going on? Let's have a look. So I've graphed my three functions here. Which one is which? So this first one here is our parent function. So that's y equals, and you see I used color just to help us see this a little bit better, equals x squared plus 0x. Then here we've got y equals x squared plus 4x. And then this other one, y equals x squared minus 6x. And if you get a straight edge out, you can actually draw your axis of symmetry for each function. So for the red function here, y equals x squared plus 4x, your axis of symmetry is this vertical line, and it's going through negative 2. For our parent function, the axis of symmetry is at x equals 0. And for the green function here, y equals x squared minus 6x, your axis of symmetry is going through x equals positive 3. So if you look at your b value here, divide it by 2 and change the sign, that's where the axis of symmetry is coming from. So let's write this out. Changing the value of b changes the location of the parabola's line of symmetry. For b equals positive 4, the line moves 4 divided by 2, or 2 units to the left. If b equals negative 6, the line moves 6 divided by 2, or 3 units to the right. In general, the parabola's line of symmetry moves b divided by 2 units left if b is greater than 0, another way of saying positive. B divided by 2 units right if b is less than 0, or negative. Okay, let's take a look at the last example here, the last exploration. How does changing the value of c affect the graph of the relation? And you can see our c value is the value at the very end, and before we actually put this into our calculators, you can anticipate what's going to happen. Similarly to when you have the equation of a line, y equals mx plus b, it's that constant at the end, and a line, the constant at the end represents your y-intercept. And that's going to be the same here. Sorry I gave it away. So let's try this out in our graphing calculators. So putting in, oh, I didn't have to get rid of the parent function, but I did. So we put back in y equals x squared, and then put in y equals x squared plus 3, and hit trace. And you can see our parent function and then plus 3. And in this case, it's moving our graph up, right? And now it's going through that positive 3 on our y-axis. If I go and do that again for the next function, x squared minus 3, and trace that one, there, it's down at negative 3. So let's go ahead and draw that in our notes and then write our conclusion statement there. Now in this example, and in the previous example, I didn't state it, but the width hasn't changed, even though in my drawings they're not exactly to scale. There's nothing happening to the width unless we changed what? If you go back to the other page, the a value, right? That's the only thing that's changing, is when we change the coefficient in front of x squared, and we haven't done that in any of these other examples. So just make note of that all we're doing here is we're changing these y-intercepts. So this one here went through at positive 3, this one here is at 0, 0, and down here this is at negative 3. So in all of these graphs, again, the width stayed the same. The value of c shifts the graph up and down. It physically is moving our graph up and down. And that c value corresponds to our y-intercept. So if we have a c value of positive 3, the y-intercept is positive 3. If we have a c value of negative 3, then the y-intercept is negative 3. And that concludes us going through all the different parts of the quadratic function and how it affects our graph, the parabola, when we put it on in our calculators or graph it on a plane. So, to take a look at the next page, and we've got a second example here. I'm going to ask you to do this one on your own. It says the graphs of the three quadratic relations are shown. Predict possible values a, b, and c in the equation for each graph. So try that on your own, going through what we did in example 1, those explorations. And you can also use the summary down here to help you out, and we'll go over that example together in class. Thanks for joining me.